We've looked at Taylor series and Maclaurin series and how to build them and finding limits and finding sums. And what we're going to look at is using Taylor series to integrate. So if you look at this problem, it says the integral of e to the negative x squared. And the problem with that is that's not something you can integrate. You can use trapezoid midpoint Simpson's rule to estimate, but you can also use Taylor series to estimate. So we're going to start off with looking at it as an infinite series, and then to a specific value correct within an error of 0.001. So let's look at it first of all as an indefinite integral. So before we start, let's consider e to the x using our fancy handy dandy chart that we used in the other one. So if you'll take a second, pause, pull that out. So we're going to say that e to the x equals the series from n equals 0 to infinity, x to the n over n factorial. And this equals 1 plus x over 1 factorial plus x squared over 2 factorial plus x to the third over 3 factorial plus dot, dot, dot. And out here somewhere we have x to the n over n factorial plus dot, dot, dot. So what we really want to look at here is e to the negative x squared. So this means that we're going to take the same series, but instead of x to the n, we're going to put negative x squared to the n over n factorial. So this is 1 plus negative x squared over 1 factorial, which is 1, plus negative x squared over 2 factorial, plus negative x squared to the third over 3 factorial, plus, and out to the side somewhere, dot, 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 we have negative x squared to the n over n factorial plus dot, dot, dot. So when we work this out a little bit nicer, we have the series from n equals 0 to infinity. And we have negative 1 to the n, which makes it alternating, x to the 2n over n factorial. That's our nice, pretty summation. Sometimes it's helpful, sometimes it's not. And then we have 1. This is actually not a plus because we have minus x squared. So we have minus x squared over 1 factorial. I'm going to keep it in that format. And then when you square the next one, you get x to the fourth over 2 factorial minus x to the sixth over 3 factorial plus dot, dot, dot. Let's go ahead and pull this over. It keeps bouncing on me. This would be negative 1 to the n, x to the 2n over n factorial plus dot, dot, dot. So when we integrate this, when we want to integrate e to the negative x squared, maybe I should have zoomed that a little bit differently. So this is e to the negative x squared. So if we're going to integrate both sides, I'm going to just throw it on here. Dx equals the integral of this with respect to x equals the integral here with respect to x. So this means the integral of e to the negative x squared equals, now I'm going to skip the middle portion right here and come back to it. So I'm going to leave me a little bit of space. When you integrate 1, you get x. When you integrate x squared, you add 1, x to the third, and divide by the new power of 3 times 1 factorial. Plus, when you add 1 here, you get x to the fifth, divide by the new term, the new power of 5. We already have a 2 factorial underneath. Minus, add 1 to be x to the seventh over 7 times 3 factorial, plus dot, dot, dot. We have negative 1, so this becomes x to the 2n plus 1 over n factorial times 2n plus 1 plus dot, dot, dot. I shouldn't try to squeeze it in probably, but I am. So it looks like that. And then plus c, somewhere in there. We tend to write the c up front. I forget it every single time. So I would rewrite it to say c plus. And then all the stuff that follows. So we would say c plus x minus x to the third over 3 plus 1, 3 times 1 factorial, plus x to the fifth over 5 times 2 factorial, minus x to the seventh over 7 times 3 factorial, plus dot, dot, dot. I'm going to erase my plus c up here because it's in the way and write it in, I'm going to scrunch it in over here, plus c. And so then we have minus 1 to the n, minus 1 to the n, x to the 2n plus 1 over n factorial 2n plus 1 plus dot 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 plus dot dot dot. So we know there's some constant there. Now when you integrate here, if you think about it, we didn't lose any terms, so we're still going to start at n equals 0 to infinity. And when you integrate a power series, the n doesn't change. You just add 1 to the x to the 2n plus 1, and then divide by the new power, 2n plus 1. And here we have n factorial. So you can see that these two terms, this general term here, matches this general term here. But it's helpful when you're estimating the sum to work with the terms rather than the whole series. But if you're asked to integrate, you kind of want to look at what they're looking for. I wouldn't mind if you did the answer in the box right here, or if you did it term by term. Some people think it's easier to see it term by term. If you have to evaluate the integral, you're going to want to go term by term. So what we're going to do is we're going to pick up this red right here. I'm going to slide all this up because the part B said to integrate from 0 to 1 e to the negative x squared with respect to x. So we already know that that's c plus x minus x to the third over 3 times 1 factorial plus, I'm going to put a big bracket here, plus x to the fifth over 5 times 2 factorial minus x to the seventh over 7 times 3 factorial. Let's put one more for good measure, x to the ninth over 9 times, the next one would be 4 factorial following the patterns, minus dot dot dot, and the bounds go from 0 to 1. So now, because it's a definite integral, we no longer have the plus c. We would have left that off. So let's go ahead and cross that off so it's not confusing. Now, just like when you do any other integral, you're going to do f of 1. Let me write that correctly. F of 1 minus f of 0. But let's talk about f of 0. If I put 0 in for x, that means that we have 0 here and here and here and here and here and so forth. So f of 0 is 0 because there's an x going everywhere 0 is. So that's not really necessary. So let's plug in f of 1 for x. So when we plug that in, we have this equals, let's go ahead and put it equals here. So the integral equals 1 minus x is 1. So we're going to say 1 to the third, which is 1 over 3, plus 1 to the fifth is 1 over 5 times 2, minus 1 to the seventh is 1 over 7 times 6, 3 factorial is 6, plus 1 to the ninth is 1 over 9 times 4 factorial is 24, minus dot dot dot. So this is looking pretty good. We have 1 minus 1/3 plus 1 over 10 minus 1 over 42 plus 1 over 216 minus dot dot dot. If my math is right, we're going to hope and pray it is. Now, it was important that we notice that it said correct to within an error of 0.001, so that the error is 0.001. So what we're going to do is we're going to look at the decimals here. We have 1 minus 0.3 repeating. Let's just call it 0.3 repeating. We're talking about 10. Here our error is thousandths place, so let's go 4 decimal places here. Plus 1/10 is 0.10. Minus, well, let me pull out my calculator because I don't know 1 divided by 42 right off the top of my head. So 1 divided by 42 is 0.02381. And then I have 1 over 216. So 1 divided by 216 is 0.00463. Now this number is still bigger. This is how the error is determined. This number is still bigger than 0.001. So we need to find another place. If we were to continue our integral up here, back up here, let's go ahead and erase and add to it because our number is still bigger than the error allowed. So I'm going to explain to you what that means in just a minute. But we're going to go ahead and make this x to the 11th over 11 times 5 factorial. And let's add an x to the 12th. So we got x to the 12th. That's not even right. We're counting by odds. So let's make it x to the 13th. Notice the pattern on the top, 1, 3, 5, 7, 9, 11, 13. There we go, 13 times 6 factorial minus dot, dot, dot from 0 to 1. We should be set now, but let's make sure. So when we come down to this first green line where we're plugging in our 1, we would have 1 to the 11th is 1, and 11 times 120. And then we would have 1 to the 13th is 1, and 13 times 720. Yeah, let's not go into how I know that. So 1 over 11 times 120 is 1320. And 13 times 720 is 9360. So then we would subtract, let's pick up with this red one. 1 divided by 1320 is, I got 7.57. I got 7.5757 repeating times 10 to the, this would technically be an 8 when you round it off, times 10 to the minus 4. So remember, we move our decimal point over 4 places, 1, 2, 3, 4. The screen keeps sliding. So we have 0.00076. Now, we can go ahead and do I'm going to erase this and add the last term because we did 2 just in case. So I'm going to add 1 divided by 9360 is 0.00011 minus dot, dot, dot. Well, that got really big. Minus dot, dot, dot. Okay, now, when you're looking at an error of 0.001, this means everything smaller than this is going to get left off, so it doesn't matter. So if you look at this one, it's smaller than that. There's a theorem that says that back in the alternating series test. And this number is also smaller than 0.001. How do you know? Compare them. So 0.0010 is bigger than 0.007, so it also does not matter in the 3 decimal places. So now we're going to combine these terms. I have 1 minus 0.43 plus 0.10 minus 0.02381 plus 0.00463. Now, you might be a little bit off from what they have. I have exactly what they have. I have 0.7475. So we're going to round to 4 decimal places. And you go one farther than the error, but you can see that that's not going to affect your answer when you get these very small decimals down here. They don't affect the sum anymore. The numbers become so small, if you were to keep looking at them, the numbers become small enough that they don't affect the sum. So we don't include them in the summation. Okay, hopefully that makes sense. Let's look at another one. And let's do the integral from 0 to 0.5. Let's do 0.6. It says sine x squared dx. I'm going to try not to destroy my screen this time. So let's start with, we know that sine of x equals, I'm not going to use the summation because we have bounds. So what we're going to need to find is an approximation. We're approximating this. Now notice you can't integrate this. You can't use u sub. You can't use trig, any of your methods. This is something that we can't find the antiderivative of. So you would have to use an approximation. And the series approximation is not bad. So sine of x equals x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Well, when I'm trying to decide how many places to use, I guess the error would be important. The error will always be given to you, and the error on this one, it says the error is less than 10 to the negative 5th, which is 4 decimal places and then a 1. So that's pretty small. Let's list several of these terms. Let's say plus x to the 9th over 9 factorial, minus x to the 11th over 11 factorial. Generally, you need at least as many terms as there are decimal places. That's just a pattern I've recognized. I can't guarantee it. So we have 1, 2, 3, 4, 5, 6. We probably are good. Let's add 1 or 2 more for good measure because I don't want to have to come back up and do it again. So we have x to the 13th over 13 factorial minus x to the 15th over 15 factorial plus dot, dot, dot. I tell you I think I'm good, and then I go ahead and add a few more. So let me think about that for a second. Okay, I'm going to go with the pattern I told you. Because it says x to the 5th, generally you can do about the first 5 or 6 terms. So here's 1, 2, 3, 4, 5. You with me there? So let's pick up one more for good measure. And let's go ahead and erase these. Oh, it won't let me erase today. So let's go ahead and erase these and put plus dot, dot, dot and live in the pattern I've recognized because it'll make your life easier. We can always go add some more terms if we need them, right? My dot, dot, dots ran together. Not good notation. Let's try again. Notation's a big thing. It explains exactly what you're doing. All right, so now we have sine of x squared. So what do we do with that? Hopefully you said we're going to replace all the x's with x squared. It's a composite function. So here we have x squared to the 3rd power. I'm going to go ahead and call it x to the 6th over 3 factorial. Plus x squared to the 5th is x to the 10th over 5 factorial. X squared to the 7th is x to the 14th over 7 factorial. X squared to the 9th is x to the 18th over 9 factorial. That's going to be hard to read in a minute, so yes, let's fix it now. Do you ever have those moments? Totally. And then minus x to the 22nd. I really don't think we need this one. X to the 22nd, 2 times 11 is 22 over 11 factorial plus dot, dot, dot. So now we're going to integrate this. We're going to say the integral from 0 to 0.6 of sine of x squared dx. Now when we integrate with respect to x, that means the only thing that changes is the power of x. So this becomes x to the 3rd over 3. Minus this becomes x to the 7th, and you divide by the 7, but you already have a 3 factorial down there. Plus x to the 10 plus 1 is 11 over 11 times 5 factorial. Minus x to the 15th over 15 times 7 factorial. These numbers are getting small in the denominator. Do you see this? X to the 18th becomes x to the 19th, and we have 19 times 9 factorial. Minus x to the 23 over 23 times 11 factorial plus dot, dot, dot. Plus c. We don't have plus c because we're doing bounds. And our bounds are from 0 to 0.6. Now again, think about so we're doing f of 0.6 minus f of 0, just like we normally do. Let's put a parentheses on it. And note, f of 0 is 0 because you're putting a 0 everywhere there's an x. So all of those terms have zeros on the top, therefore it is 0. So let's talk about f of 0.6, which is really the part we need. So we're going to say this is 0.6 to the 3rd over 3 minus 0.6 to the 7th over 7 times 3 factorial plus 0.6 to the 11th over 11 times 5 factorial minus 0.6 to the 15th over 15 times 7 factorial plus 0.6 to the 19th over 19 times 9 factorial minus 0.6 to the 23rd over 23 times 11 factorial plus dot, dot, dot. We could add them in if we need to, but I really don't think we are. Remember, our error is 10 to the minus 5. So our error, again, I'm going to write it here, is 10 to the minus 5. All right, so we got to be within that error. So grab your handy dandy calculator and hit pause and fill in those numbers. And just go ahead and go straight for the decimal because they are crazy decimals. Okay, so I'm going to hit pause and fill mine in. You hit pause and fill yours in, and then we'll compare. Okay, I got to the point where I was like, I don't need to do them all. Hopefully you did as well. Remember I told you you probably need like 5 terms or less. So remember our error is 10 to the minus 5. So when we look at this number way out here, this number is 6.2194 times 10 to the minus 9th. That is not going to affect that sum. It is way too small. This number, the one before it, is actually times 10 to the minus 6. So it is smaller than our error. So our answer is the combination of these two terms. Make sure you go out past the 5th decimal place. So do like 6, 7, 8 decimal places. But if you combine those two numbers, then the final answer is 0.07133, which is perfectly correct. And round to how many ever decimal places your platform says to round to. So the deal here is that when you're doing these, I'm going to back up, take a moment, notice that this is our answer, and I'm going to back up. When you're using Taylor series to approximate, the first thing you're going to do is take your known value and make it match whatever is inside the integrand. So this says the integral of sine x squared. And then list out those terms here. See how we list out those terms? And then when you integrate, just integrate each term by x because that's going to make very much sense. And then as usual, we evaluate using bounds. And we throw out values that are smaller than the error based on a theorem earlier in the chapter. Okay? If you have any questions, let me know. I hope this is a helpful video and have a great day.